special person because he was a student many years ago, and I think you were the first student who was able to work with all the professors, all the senior people in the then Institute for Theoretical Physics at the time when you were here. So, you know, his PhD was formally supervised by Moore, but he worked with Romain, he was already here with me, with George. We wrote papers all together. And so it was, of course, a very brilliant student. In fact, you know, right after he got a PhD in 2010, he went straight to the US, to the University of Chicago, KCP, with a fellowship working with Andrei Kratsov and Nick Medin. And then after that, he was a postdoc in Surrey, in the UK, for another 3 years. And then we have, you know, like 2016 or something, and then he moved back to his own country in Sweden, when he is a tenured professor since years, and he's going to talk today about one of these topics that he has worked on for a long time, galaxy formation. But Oscar has also done really pioneering work at really at the interface between star and galaxy formation. I think today we are going to hear about that in the context of early galactic disks, a challenge for galaxy formation theory.
Yeah, thanks a lot, Lucio. Yeah, thanks for that generous introduction. Yeah, it's very nice to be back. This is a room where I actually defended my thesis in, you know, the same spot. So maybe that adds an extra bit of, you know, level of nervousness somehow, right? You know, George is not with us anymore, unfortunately. He was sitting over there as well, asking questions. So it's great to be here. So I'll talk about early galactic disks. I mean, this is a challenge to galactic information theory. There's something that has been brought up. It's been a hot topic now for a couple of years, I would say. And so I will discuss this in light of the new James Webb and ALMA observations. I will connect a few different topics that are indeed connected. How turbulent can disks really get? You know, the physics of disks in themselves. And the formation of disks. Is there actually a disagreement in the galaxy formation community? Is there one or not? Then I want to make some connections to the Milky Way, thick and thin stellar disks. Can we see clues to this sort of early formation stage in the Milky Way data? And if I have time, I will mention things like bars and bulge formation, and maybe even black holes if you have time. So at the end of my talk, okay? Okay, so the premise for this is this, okay? So before we had ALMA and James Webb Telescope, we had the Hubble Space Telescope revealing these sort of local rest frame UV bright spots, right? Or massive star clusters essentially at high redshift. So what we had in that disk galaxies look extremely clumpy, okay? And this is all was a prevailing picture for many years. Okay? What happened since we got the James Webb and ALMA installed is that suddenly now we have rest frame optical imaging, okay? And suddenly we're seeing what we think is disk components around these sort of more disturbed sort of morphologies, okay? So disks seem to be much more prevalent than we've previously thought. So we can also see the gas components of this using ALMA, for example, at very high redshift. And this is now changing the way we think about how early on in the universe can disks emerge. Okay? So here's another way of looking at this. This is now the fraction of disks versus redshift. Here we have the sort of previous understanding that we had that disks form late, and it goes up to some sort of fairly high fraction of redshift 0. Now with James Webb, we're just filling in this, right? And it turns out that almost half of galaxies, even at redshift 4 or 5, or have something that looks like a disk component. Okay? And some report like significant fractions up to redshift 9 even, right, in terms of disks. So that's not a lot of time in order to sort of get the disk to form, but also to survive from all the sort of high redshift merging and such things. Here's one example. HST reveals something like a little lump here. Now when we can go to the rest from optical, we see something here that could be a disk component around this, okay, seen edge on. Other examples are like this. These things that would be sort of very lumpy structures could be dwarf galaxies merging. It looks a bit more actually like a disk with even spiral structure connecting these lumps, right? So it's quite exciting to see this happening in such an early epoch. Yeah. So the question now is, what about dynamics? Okay, so the way we do this in the extragalactic community is that we talk about the ratio between the rotational velocity, okay, and the turbulence level, sigma. So V over sigma is this ratio, how much is in rotation versus just turbulence, vertical turbulence, okay? So rotation, vertical turbulence, and it seems like disks can be quite, dynamically and kinematically cold, even at very high redshift. So there are reports now of V over sigma levels of 10, which we should compare to local spirals. So in local stars like the Milky Way, the H1 layer in the Milky Way is around 10 kilometers per second, the rotational velocity around 200, so V over sigma is 20. Okay? And if you can do this all the way at redshift 3 or 4, right, approaching these values, it's quite, it's quite peculiar, okay? Because again, in mergers, interactions, you have to have enough angular momentum to create these disks. Right? So how does this happen? Yeah. And this has become a fairly controversial plot in the last year or so by Masha Kohandel. She plotted V over sigma here versus redshift. What we have over here is observational data from ALMA, from C2 emission line and O3 for James Webb Telescope. So tracing basically cold and slightly warm gas, okay? These are the data points. So there's a big population, a family of galaxies that have very large values, right? Okay? While the points or the lines I'm showing here are the median relation from the illustrious TNG50 large volume simulation. Okay? And this would be, it's a great result before we got James Webb, but now we get, where we have a declining fraction of disks, right? As we go to higher redshift. But this now seems to be in very strong tension to the actual data. Okay? So is this a big problem or not? Are we missing something in our theories that can produce these kind of, rotating disks? Okay, so let's first, before I go into more details of this, let's talk about the behavior of high redshift disks and the importance of doing actual proper one-to-one comparisons. Okay, and what I want to do here is first is to say, like, a few global properties of high redshift disks that we know so far. One is that they are more turbulent, okay, which I already mentioned. Here's one from Hanna Ibler in 2019, where they look at the turbulent velocity dispersion of the gas in galaxies as a function of redshift. And these are different sort of gas tracers. Some of this is H alpha, so warm gas, and some of this is CO. Okay? But it seems to be increased by a factor of a few compared to local universe galaxies. Okay? So they are more turbulent. They are also more gas-rich. This is Amélie Santonge's compilation from different surveys, okay, showing that they go to higher redshift, these galaxies are just much more gas-rich. We don't have a complete census of this yet. These are fairly biased in some sense. They're looking at more massive systems that they can see, but still there are these kind of data points or these sort of data that we have to confront our models to. Okay? So what happens if we have turbulent and gas-rich galaxies? What's the nature of such objects? And then this is an occasion where we want to simplify the problem, right? So before we go to the cosmological models, let's do something much more simple. Okay? So let's set up isolated models of galaxies and do this at a very high resolution. Okay? So now let's model something that could be a local universe galaxy like this, 10% gas fraction, kind of what the Milky Way has. And then we simply just increase the gas fraction and allow it to develop more turbulence, more clumps, right? And behave as a high redshift galaxy and study what is doing what, right? What is driving the turbulence. That's what we've done now with the Ramses code here. And we have been doing a lot of different experiments in this kind of setups, right? I think it's good to extract this from cosmology and go back and do it in a simple sense, right? And what we found is that there's an interesting thing in terms of the stability of these galaxies. That once you go about 20% or so gas fraction, you run into something where the gas drives the instabilities and you get these big clumps. And once you go to the less than 15-20% gas fraction, you go into local universe spiral-like system. Very striking, transition, right? At some typical gas fraction, and it comes down to gravitational instabilities. Indeed, we have done a few papers on this, okay? So one with Florent Renaud, that he was leading on this, where we studied this as a function of scale, which I don't have time to get into. One that's, this amazing paper by Flor, of course, right? Where we looked at how we can map this turbulence to the stellar kinematics and actual real observations. And then one I will talk a bit more about now is if it's the feedback in the galaxies or the gravity that's driving the turbulence in these systems, okay? And what's the limit of how much turbulence you can drive? If we don't know this, we cannot talk about the high redshift universe turbulence, right? If we don't know how a disk should behave when it's sitting alone, right? And then you have to add mergers and complexities to this model as you go, as you move forward. Yeah. Okay, so what drives ISM turbulence and how is there a limit to how much turbulence we can drive? Yeah. So this is a plot that was made by a student of mine, Tim A. Deschamps, the most difficult to pronounce name in the world, I heard from colleagues. And this is velocity dispersion versus star formation rate of galaxies. And these are just taken from the literature. And this is a plot that's become quite popular in work by Mark Krumholtz and basically Burkhardt and collaborators as well. That as you go to the more star-bursting systems, so more higher rates of star formation, you have this incredible increase in the turbulence level. So that's the data, and it's actually a mix of different gas tracers here, okay? And there's been a lot of analytical work trying to understand this relation. Okay? And this work has focused on like basically getting lines to fit this data. Right? So you can do this by assuming some stability criterion and seeing like how much turbulence do you need to drive in order to stabilize the disk, how much feedback is pushing the gas around, and try to get these lines to go through the data points, like a good theorist should do, right? The problem with this is that this is very heterogeneous data. So if you now do a log plot of this, so that's not a cool technology, it's more like just a log in the plot. And what happens then is that you see then that the ionized gas behaves very differently from the molecular and neutral gas, okay? Also, most of these very high redshifts, high star formation rate points, or mostly high star formation rate points are high redshift galaxies. So many of these are simply interacting, they're messy, and it's not clear then how you do actually a nice disk sort of model for this, right? So beam smearing, right, where we actually are mixing in we're mixing rotational velocities to turbulent motions, will be a huge problem. And this is work by the Teodoro and Filippo Frattinalli and others for a long time. Right? Okay, so let's explore this a bit. Is this something we want to just make a model for and try to understand, or are we actually fooling ourselves, right, with this data set? Okay? So one thing to do is to make a simple test. So we do the same thing as I said before. We set up an isolated disk, and then we turn off the feedback with a fragment. We have a gravity-driven scenario, right? We just have feedback. It's not efficient for some reason. These clumps are very dense. You can motivate it this way. And then that's an extreme case. And then we have one where we let the regulation be done by stellar feedback processes. This is something we have developed for quite a while. We have all of these fancy supernova methods, to inject energy and momentum and radiation pressure and such things, right? So now we're regulating it in some way, and you can see the big difference. Okay? Now, what happens now? If I now go back to these data sets and I just compute what's the velocity dispersion I can drive in this galaxy, the gravity only one. Okay. So now these are now the sort of shaded region here is the patches of the galaxy. And this is the average velocity dispersion. And it turns out to be like 10, 15, very low, right? It's overlapping with the neutral gas data. So it kind of works without any of this feedback. Okay. Then I add the feedback and I get basically no difference. Okay. I get the same result essentially, okay, at a slightly different rate of star formation because you're regulating differently. And so this is essentially how disks behave, right? Like if you fragment, you will have to stabilize the disk from cloud-cloud interactions and stable, and get the random motions you need for the disk to sort of survive. If you do it with feedback, it's easier. You have a different kind of pressure, but the same turbulence can be measured, right, as an observer. Okay? So, and what happens in the end is like you can actually go through this sort of stability analysis approach and look for things like 200 cube parameter and such things, and you always get the same for these kind of objects, right? There's no difference in how these behave. But what if you add more gas and make it a bit more tough for the model to survive? That's what we did here. So now this is a high redshift analog at a high gas factor, 50%, right? Without the feedback and with feedback. Again, there's no difference. So this one fragments violently, okay, into lumps. This one will also, but it will also push gas around much more with the supernovae and such things. Right? So here, and so the takeaway is that it's very difficult to disentangle the processes that drive turbulence, right? Because you can get it in different ways, and you have to break it with other observables in such way, right? Like Starcaster mass functions and these. Okay? And the other takeaway of this is that you can't really, if you had done other experiments with even more crazy gas factors, you can't drive turbulence to more than 40, 50 kilometers per second or something. It's impossible to produce these points unless we beam smear or something like this. We make a mock observation and we are adding rotation to our to our patch of the galaxy. Okay? So that's a big problem. And so what we did in this work is say, look, okay, we have to be careful what we're talking about. So what is the turbulence in the different gas phases? Because it's a very multi-phase system, this galaxy. So now we did mock CO H1 data, okay, and then we compared to the relevant data set, right? So here we compare the turbulence levels now to the CO data we have. These are some very strange sort of high redshift measurements. These are from visual inspection, just like mergers and interactions. They're very non-disk-like. Okay, so these are messy. And here's the H1 data that we have from the local universe. Okay, so we are matching basically up this. But if we go to the warm phase, that is the shock heated or it's the radiation heated gas, then we can get very large values of velocity dispersions. But this gas is not really ISM turbulence. A lot of this is just outflows, right? Things that go out of the galaxy. So we should not connect this with turbulence in a disk, but more like off plane sort of motions of the gas, right?
Can I ask how this is measured in high redshift galaxies? It's sigma gas.
Yeah, so this is just so here it's just the line profile, right? You have an H alpha emission line, and you measure the width of this. Yeah. And what you have to do, that would be the line of sight one, but then you can try to do a disk sort of inclination correction for this, right? And then you want you want to have the data cube, so you want to have the position, and then the sort of the spectral information or the in velocity bins, right? And then you can reconstruct this using something like 3D Barolo, which is what Filippo Fraternali has pioneered. And then in the end, you rotate the galaxy into its proper sort of proper spin axis, let's say. And then from there, you can compute the velocity dispersion of the gas. But it comes down to the line width, basically, of the H alpha.
You don't have a resolved galaxy at these redshifts.
No, yeah. So that's right. So for a lot of these, for some of these where you have kiloparsec resolution, you do it in patches and you intensity weight them. Yeah. Then local universe systems, like in the FANG survey, for example, it's all quite well resolved onto 60 particle scales. A lot of these are just averages, right? As you say, right, of entire galaxies.
But in the CO, you have this very low velocity, right? The very high velocities, you're saying, they're the H alpha.
Yeah. Exactly. So most of the really high velocities here are simply just diffuse gas, it turns out. Yeah. And it turns out that you don't need that much energy to power this, right? 10% of the supernova energy, or actually the turbulent energy, is in the diffuse phase. So it's not really that important. It's not very inert gas. It's quite, it's diffuse gas about to leave the galaxy, most of it. So the point of this is that which I will get to in a second also, right, is that this offset between different phases needs to be understood if you're going to talk about stability or turbulence levels, right? We cannot say that this is the ISM turbulence. You have to consider the different gas phases. And actually here is where you see a difference, right? If you have to turn off the feedback, you can't power this diffuse gas. So this is a signature of what's driving actually turbulence, right? But you have to go to these warm gas phases. And right now there's a lot, with James Webb, there's a lot of emission line modeling work that's being done from more highly ionized species to gas tracing more the cold phase. And here is where we can actually understand the physics of what's driving turbulence better, I think. So we need to have this multifaceted way of doing it. Okay, so the point is now, let's have a quick look at this one. So this is now the star forming phase, the CO, okay? And here we can't get these extreme values, right, in a disk setup, yeah? So there's a caveat for these analytical models. Absent mergers, we cannot get to the values like greater than 40, whatever, 50 kilometers per second. It's impossible. So we shouldn't try to fit lines to this. Those models cannot be correct, I think, okay? But now, but this is still a significant amount of turbulence compared to the local universe galaxies. You can actually get to something that is many tens of kilometers per second. And this brings me then to Flash, your workflow, okay, again. So this is, and this connects then to the Milky Way science, okay, which I will get to in a few minutes. So if I now plot the birth velocity dispersions of stars on the y-axis, okay, so what is these stellar populations that are born out of this sort of turbulent medium versus the high redshift, or the gas fraction. So high redshift conditions is on the right, local universe conditions on the left, okay. What I find is that the stars are generally born from this turbulent molecular gas, okay, at high velocity dispersions, okay. This is actually what we are measuring, close to what we're measuring for the thick disk of the Milky Way, okay? So you may not even need to have secular heating of stars in the disk. You can get this for free just from the conditions of the ISM. Yeah? Then we have this transition I mentioned before, right? There's a striking transition around 20% gas fraction, where you suddenly get this Milky Way thin disk kinematics, okay? 5-10 kilometers per second of the young stellar populations. And this is quite scary, right? Because it means that there's almost like a barrier against the thin disk formation. And the Milky Way, we think, has had a thin disk for maybe 8 billion years. Yeah. And so it means that the gas fraction of the Milky Way can't have stayed very high for very long, but you have to have depleted a lot of gas, stayed around here for a long time. Otherwise, we can't explain the data. So that's another sort of constraint on galaxy formation models, right? You cannot be gas rich to that close to redshift 0 if you're going to have a thin disk here, right? Okay, so moving on then to disk assembly and gas accretion. Okay, so I'm going to build the galaxies. Okay, and now here's a bit of historical stuff. It's some work I did with Ben back in 2009 and Romain Tessier. So how are galaxies fed by gas? Okay, so from theory and simulations, we know for a while now that they say early universe galaxies are likely fed by cold streams that are, these are very high accretion rates, and they can even build the disk directly like this. And as we go then to lower redshift and we build the halo mass, this is actually the line we had for this specific simulation, okay? Then we're transitioning into the hot mode where we can have a stable hot corona because the accretion shocks are just powerful enough to be sustained, right? And you're not radiating away that energy. So then suddenly we go into this hot flow kind of mode. Right? So this is the dichotomy, right? We kept gas with early redshift, high redshift, and then in the more local universe, we have hot corona feeding galaxies. Okay? Here, there's a bunch of problems, right? So there's a theoretical picture emerging. What's necessary to build disk galaxies? Okay. Here we see the stellar populations of one of my simulations. So first of all, we need this gas that accretes to be coherent in its angular momentum budget. Right? It has to be angular momentum rich, but it has to be coherent. Otherwise, if it's random, you're not going to make a compact system. Right? So it has to be accreting coherently, forming a disk. We've known that for a while. Feedback can promote this. Okay. Funnily enough, this feedback that creates turbulence and mess actually helps to promote this, right? So, and it does so, but in most star formation happens in the center of the galaxy, and by ejecting that low angular momentum gas, recycling it on large scale, and then falling back to the outskirts, you actually promote this formation. Okay. Then we also have the problem of mergers, right? So the merger rate of dark matter halos and galaxies increase at higher redshift. Okay. That means that there's actually there's a sweet spot where you've had the last major merger, okay, where you're no longer where you're sure you won't be disrupted anymore by something like a major galaxy collision. And it happens to be somewhere around, a few 10 to 11 solar masses for the virial mass of the dark matter halo. It's like a golden mass where most galaxies now can start building their disks, in a relaxed sense, right, without being disrupted by mergers. Then there's a big discussion going on right now, like how do you get, that can build disks, but a thin disk, like razor thin disk, like how do you get this, okay? So there's a push from certain part of the community that you actually need to have the circumgalactic medium to viralize, meaning you have to have a hot corona in place. Otherwise, you only get thick, weird disks. And this is not an agreement in the community yet, but it's something that's being developed. Phil Hopkins had this monster paper out last year, I think it was published this year, where he said a lot of this doesn't make sense. You need to actually have a steepening of the gravitational potential in the center of the halo. A well-defined, deep potential well, like a bulge basically, right? Or a bit more cuspy dark matter halo. Then you can have a guiding center to form the disk around. Okay? If you don't have this, you have chaotic accretion, and it's just sloshing around, and there's no stable point. Okay? And then we have other people like Vadim Semenov, who says everything happens at the same time, and it's not easy to separate these things. Okay? So this is where we are a bit now. Like there are these processes we think are important, but we haven't yet been able to separate them. Probably they all play a role. Okay? So I will go a bit more into detail what I think is going on here. Okay? First thing to just mention here is some disagreements in the community. Okay, so then the disk formation and the CGM. These are examples from the FIRE collaboration. This is Phil Hopkins, his PI on this. And something that happens here when it comes to disk formation is that they again found that you need to have long cooling times in the halo around the galaxy in order to get, compared to the free fall time, the time it takes from gas to actually, sink in, assuming there's no pressure gradient or anything like this. Okay? This ratio between T-cool and TFF has to be large. Right? And you see it here, right? So you see here that you have an early phase here, redshift, 1 or so, where you have very short cooling times. Gas accretes, it's a complete mess. The galaxy explodes continuously. Okay, you can't get these sort of high V over sigma systems. It's low, it's crazy. Star formation rate is bursty. It just reacts too much to the accretion. And once you have realized the halo, you have a hot corona in place, then you settle the disk. Okay? The problem here, of course, as you see here, that this is redshift 0.3. So this is not, this happened very, very late, right, in this evolution. Okay? So it's a mess early on, and then in the last few billion years, you managed to form a disk. Okay? Here is another way of presenting this. So yeah, in these fire models, you form a thin disk, V over sigma greater than unity, very late, past 3 billion years. And you can see it here. This is actually the radial profile of the V over sigma, okay? And when it's getting to, close to 10 is where you have a Milky Way-like system, let's say, right? And here is color-coded then by this sort of, the cooling rate timescale and the freefall timescale. So when you go into the red or towards the red, you see this transition. Yeah? But again, this is happening in the past few billion years, which means that we cannot, I don't think we can explain local spirals and the age of the Milky Way thin disk this way, right? This is way too late. However, in these models, the more massive galaxies, the very massive halos, a redshift 0, they can form very thin disks, quite thin disks in the early universe. So in this setup, it's the big halos that we are seeing with James Webb. That's the takeaway from this one. But then we have this plot again, where I showed you earlier on from Marshall Cohandle, right? Where the TNG50 models, they actually could not reproduce the high V over sigma values, the high redshift. Here's another disagreement. We have a Serra simulation from Palatini, Andrea Ferrara, and others here. These are the simulation lines they have here. The underlying points are the actual observations. And they will say, look, this is no problem. We can actually get thin galactic disks even at very low stellar masses here. So again, like we here is not trivial. So what the difference is at all, right? It's just a stark disagreement, apparently. Yeah.
Can I ask? Sorry.
Yes.
So why is this better? Because the data is all over the place.
Yeah. So the thing is, like, okay. So the data is all over the place, okay. But the fact that you're not sampling solar, right, at all, right? The high V over sigma system, right? We should say this is the median relation. There will likely be some data points that make it up here, and we don't yet know. And this is why it's an ongoing sort of debate, right? We don't yet know what is the full sort of mass complete sample of galaxies here. Right? We don't know this yet. Right? But the ones that are starting to pop up now, they're all quite disky, or many of them quite disky. I should say that it's all over the place. Most of these sort of high V over sigma data points come from the ALMA cold ISM measurements, right? If you go to the warm measurements, the James Webb one from the O3, they tend to be a bit lower for the reasons I said before, right? That you're tracing the warm outflow components, let's say. Right? But anyway, so these exist. The fact that they even exist is one of these big problems, right? That it's very peculiar how they can form this early. But then, okay, then we can do the make a bit of a systematic study here, right? And say, okay, what happens now if we take one of these TNG50 models, Zoom simulations, and we run it with another code, right? This is the ART code now. This is adaptive measure refinement code. This is work that Vadim Semenov had out a few weeks ago now. So he take the same initial conditions, ran them with different codes. One that cools it down to 10 Kelvin to get a cold ISM, that's the ART one, and then the standard TNG50. And the reason here is not to expose necessarily like, fundamental problems or anything like this. It's more to show like what's the actual, what happens if you allow the galaxy to settle more, cool more, like the gas can cool more. Yeah. So this is what it looks like. It's only run for a few billion years. And it both looks quite messy, of course, but already here you can see there's a difference in terms of the central structure here. Okay, it's a rinsing or something. Here's the outcome of this, right? This exercise, right? The ART one here, we have a disk, I guess, right? So here, a turbulent disk. TNG50 produces something like a blobby morphology. And the point that was made at least by Vadim here is to say, like, look, even a Milky Way object that's quite a low mass halo, or a low stellar mass at this redshift, a billion solar masses, can actually, can be compatible with already the objects that we are seeing in observations, right? So the Milky Way galaxy could be one of these objects if you actually get the gas to cool and have high resolution ISM, which is not the case if you have a subgrid model for ISM. That's basically the takeaway, right? So essentially, the outcome of this again is to say this controversy of high V over sigma systems. It's I don't think it is a problem. Right? It just comes down to how we model the stellar medium in simulations, right? And I think most models would probably agree that once we go down to a few particle resolution, particle resolution in the ISM, we get cooling to 10 Kelvin or so, we ought to be able to reveal more of these objects. Okay? So it's not a fundamental problem in the field, I would say. Yeah.
So here the PNG model was run. It's the same resolution in PNG.
It was run exactly the same as in TNG, just to make it to show that it's what you expect from that kind of setup, right? It wasn't designed to do the science, right? But if you do it now with more expensive, high resolution models, of course you get things to be those disks emerge. That's basically the point. Yeah. Okay, all right, Robert. Yeah.
Yeah. So it's not, of course, just the resolution and the cooling, right? It's also the feedback. Right, because like, as you said, right,
I agree.
For instance, it's a challenge to get.
I know you're yeah. It's a whole cycling.
Yeah.
It's even things like how many metals do you put in how much metallicity do you have in the CGM, for example, right? Like is the cooling rates large enough to prevent stable shocks and these things? Yes, it's a whole cycle. I agree. So they haven't yet teased out the differences. I agree with that. Yeah. Okay, so let's in the last sort of 15 minutes or so, let me connect a bit the high to low redshifts now. So are there clues in the Milky Way, in the actual Milky Way of this early phase? But how do we get from this early phase to the now stable, safe environment that we live in today, right? The Milky Way. Okay. So this goes into the topic of old thick disks and young thin stellar disks. Right? So now I talk about the gas a lot now. Let's talk about the actual stellar populations now. Okay. So start with a simulation slide here. This is a project I've been working on for quite a while now. It's called the Vintergatan project. Vintergatan is Swedish for Milky Way, so winter streets. Okay. And here are some mock HST observations, and you can see there's a wide variety of morphologies in these objects. And so this is cosmological zoom simulations, Milky Way like halos using the Ramses code. Again, this is to illustrate, it goes to your point, Robert, right? That they are similar galaxy formation physics here as in these fire models, but the feedback operates very differently. It's very less disruptive, right? So there's something we don't yet understand why.
No, I find nice that it's called Vintergatan.
Yeah. I agree. We haven't
You never see the Milky Way in summer, do you?
No, that's the thing. Yeah, no. In the summer, no. It's Italy. We are screwed. Yeah. Here we have so here now I'm going to plot you now the rotational velocity of the gas, the cold I said, and what's the dispersion. Okay. So I do this to illustrate that there are three distinct phases of the way that these galaxies that are becoming disks evolve. Okay. And these have been also identified in other work. Belekrov, Kravtsov, Charlotte Conroy, a paper on this, Hans-Walter Rix and others, that this connects to the stellar populations, but you can see it in the gas phase as well. Okay. So here we see how the galaxy is growing. So it means like there is more rotation in blue as we go along. Early on, there's an epoch where it's as turbulent as it is rotating, let's say, but it's a blob. Okay? Then you have this early disk phase I've been talking so much about today, right? Where you start developing a protodisk, okay? We have a sigma SFU, and lots of dispersions are settling at 20, 30 kilometers per second, okay? And then you have this sort of golden mass thing I mentioned before. You have a last major merger, which is very disruptive, and then you're settling everything. It just sort of decreases the turbulent velocity dispersion. You're eating away a lot of the gas, so you're lowering the gas fraction, and now you end up with something where it's like Milky Way-like, 200 kilometers per second, 10 kilometers per second in the turbulence H1. Okay? So this is where you develop the thin disk in the last 8 billion years. And so I will walk you through a bit. What happens? What is this transition? What actually happens, right? And I think it's very useful to do some case studies here, right? And what is what makes us go from this to this, okay? And can we see something in the actual data? Okay? So in Lund, Lund has pioneered the Gaia satellite. It's Lennart Lindegren who did this already in the 80s to thought about this satellite. And it's an astrometric mission that's scanning the sky, okay? So you get very accurate positions and proper motion over 1 billion stars. And you have regular velocities and distances for many millions of stars. So it's really mapping out the Milky Way, okay? There's a follow-up near-infrared mission that's going to be hopefully launched in 30 years or something like this, but to go for the bulge stars as well, yeah? And you can combine it then with spectroscopic surveys to get the chemical elements of stars, right? And then you actually have a multidimensional view of the Milky Way, okay? And this is what we want to connect to the simulations, like what happened in the Milky Way. Okay? So that's the observer picture. I'm a theorist, so this is the Milky Way in my view, okay? Much simpler, right? And what we think is, and this is just a cartoon of how we think broadly the Milky Way is structured, right? It's a thin and extended disk that's kinematically cold, okay, mostly younger stars, okay, and it's poor in so-called alpha elements, okay, and these are basically multiples of helium nuclei, and they're produced in core collapse supernovae, okay, so supernova type 2 explosions. Then we have a thick component that's a bit smaller. It's kinematically hotter, older, and it's rich in these elements. Right? So the pollution of the ISM was quite different for some reason. The thick and thin disk, we've known about this for a while. I mean, this is Gilmore and Reed did this in the early 80s. Just from star counts, you can see that, you know, and if you go to the density of stars here, height above the disk plane, there's clearly like two components of this, right? There's a thin disk with some scale heights, and the thick disk extends further on, right? So the thick one we think is this old early stellar disk, right? That formed in high redshift, possibly. Yeah. I'm going to now focus actually on this stuff here, the chemical imprints, right? This is really something that can tell us more than one might think. Now I'll present this in this kind of peculiar plane for many people in the room probably. The ratio of the alpha elements to iron versus metallicity. This is what stellar population people call metallicity, the iron contents. So when I see this, I'm also reminded by a winter school that me and Doug went to in Mirren, I think, 20 years ago now, right? We had Francesca Mattiucci giving a presentation, and she showed these kind of plots. And I think we told each other, like, we're never going to work on this. Like, this is terrible, right? And now I'm here, right? So now, I mean, and I found it very interesting. Yeah? So what happens here is that what we expect from simple chemical evolution theory is that there's at early cosmic times, you're high in this, right? in this alpha over Fe ratio, because you produce a lot of core collapse supernovae, and you haven't yet had many type 1a supernovae, right? They come later, and they are mostly iron polluting, okay? So you're up here, then the type 1a pollution happens a billion year or few later than this, and you start to decline here, right? So this is what you ought to get. And the Milky Way actually looks like this, right? So here now, this is Thomas Bensby's work from 2014. He has some very detailed sort of spectral studies of almost 1,000 stars. And indeed, you get this kind of evolution from the Milky Way. But the Milky Way has a surprise. It has a bimodality here. Yeah? So it has actually a lot of the young stars have the metallicity reversed suddenly. Suddenly you have a low metallicity component that emerges, that is young. And Thomas, this has been a question for quite a long time. How does this happen? Is it just fresh infall that resets the metallicity? Is it radial mixing of the stars at different radii? I mean, this is what Jerry Silverwood, James Binney has been working on for a while. And what I'm going to show now is a scenario where you can get this actually from, it has to do with gas accretion. Yeah. You have to do a lot of pollution to get from a high metallicity to low metallicity. You have to add a lot of mass. So it's very difficult to do this in a way that's not related to accretion. Yeah. Okay, so this is now a case study. Okay, so what I'm going to do now is show this Wintergatan simulation. I'm going to show you now the size of the disk here versus the redshift. So what we have now is the main galaxy, the early proto Milky Way. And then this is quite a small size, 2 kiloparsecs. Okay? And then we have the last major merger up here. And when you have this basically large-scale collapse, there's a lot of inflow of gas. Okay? So it's dragging in a lot of gas, okay, from large cosmological scales. And what happens now is the following. So let me see if we can play this. So you have this thing here, you have the gas, you see now the size, how it evolves. And when you have the interaction here, there's a lot of tidal compression around the galaxy, which more or less doubles or even triples the size of this galaxy. Right? So the old disk in here, and now it's wrapping a new disk around it. Okay? And this disk actually is quite different in terms of its chemistry. So if I rotate this object, in yellow here, you see low metallicity, blue is high. Okay? And what comes in here in these streams are just a lot of low metallicity gas. Okay? And then this galaxy keeps evolving after this. Okay? So, and now it's basically built what we think it will be like a thin disk, right? It's going to keep adding gas to this object while the old early disk is almost shrinking in size here, right? The older ISM. Yeah? And this sounds almost like a fine-tuned setup, but it really isn't, right? We see this in many of our models. We see it in other models. Michael Kretschmer and Roman had a paper that indicated that this actually tends to happen, that you have this very rapid disk growth after the last major merger. The physics is this: you have optimal conditions for gas accretion because you have a very baryon-rich halo that starts to cool. It's rich in angular momentum, And there are no more disk spin flips because you're not actually, you have no more major merger. So you're staying stable, right? And this is compares quite well to fairly famous semi-analytical models like by Chiappini and others, okay, where they argue for large-scale infall to create this bimodality I mentioned. But what we have here is not really just like you don't pour the gas onto the old disk, you build a new disk around it. Right? That's the exciting thing. And now I can actually, as a theorist, I can make these plots that observers like to do, right? Where you have the metallicity versus age of the stars and the alpha over Fe versus metallicity relation that I just presented to you before, right? And we can now denote the epoch of last major merger here. And now we can see the buildup of this. So the early buildup, the oldest stellar population, that's the bulge, right? And the old, proto-disk. Then we have the epoch of last major merger here. And then what happens is that you have this low metallicity infall. So suddenly you're adding a component here, right? Low metallicity, okay? This one it starts to build here. And in this sort of other chemical plane, it resets, right? So it sits over here to the left, okay? And that's how you build this bimodality, right? You need fresh infall at low metallicity, which is not surprising because the large scale sort of distribution of gas is just low metal pore. And then you keep building this, and then you have galaxy formation as usual. There's accretion of angular momentum rich gas, and you build a disk. Okay? And in this setup, actually, in this specific one, we had the outer disk was even misaligned within a disk. But it starts to dominate quite quickly in terms of mass, and you have this torquing effect. And at redshifts closer to zero, the signature of this sort of inclination difference is gone. Yeah? Very briefly on this, right? Actually, does this make any sense? So what we have then, right, is that we have an inner disk formation like this, inner bulge, inner old disk buildup. And we have then the outer disk forming in this way. If you look at the actual Milky Way data, this is by Chuka and others from Apogee, Gaia, Kepler data. You have some machine way learning approach to get the ages of the stars. It's color-coded by the guiding center of the stars. You see it more exactly this kind of this kind of property, right? That they have an inner old disk forming early on, and the outer one forms later, essentially. Yeah. And the same sort of signature in this other chemical plane, right? Where you are developing the inner disk and the old disk, let's say, thick disk this way, and then the outer one forms in this way. And this is precisely sort of the trends that we see in the Milky Way. So from the stellar population data, I find this very exciting. We can tease out the formations known from Milky Way. So you need to have the kinematics, of course, of the stars. There's a lot of things to do there, but the chemistry of the stars themselves tell the story, right? And if the Milky Way did not have this bimodality, it would be a bit more, possibly a bit more complex, right? But it's really a smoking gun, I think, of fast gas accretion around the last major merger. Yeah. Okay, so I said if I had time, I'll talk a bit about bars as well in the last 2 or 3 minutes I have, if that's okay. So I'm only going to do this because I think it can interest a few people in this room. Okay, so this is like an added bonus to my talk, basically. Like now we are connected to these early disks, how the turbulence is generated, these things, and how we have a transition to well-behaved Milky Way galaxy. One thing that's a bit annoying, right, is that right? Formation of bars. Can this happen in thick, turbulent, high-redshift galaxies? Why am I annoyed by this? Okay? I shouldn't be, but it turns out that if you now look at go back to James Webb data, 30–40% of disks at redshift greater than 2 or 3 can actually feature spiral structure. Clumpy maybe, but spiral structure. But we used to think this was 0%, right? Now it's quite a high percentage, right? Here we have the data set. These are disk galaxies. They have these points here, these circles, right? And what happened also now is that we have very preliminary work trying to identify just visually, right? What's the bar fraction of these? It used to be really a few percent, maybe 0, right? At high redshift. Now it's more like 10–20%. These are now found in this sort of, in this jungle of galaxies, right? And this is really peculiar, right? We think of bars as this sort of thing that happens or develop more quickly in cold, dynamically cold disks, right? It's a low redshift phenomenon, we think, but suddenly they appear in the early universe as well. There's even a Nature paper out from last year, Luca Constantine, who found a Milky Way mass progenitor actually has a very, amazing linear structure that we think is a bar actually as well. So these things could be operating, and we don't know what timescales. How fast are they growing, and how fast are they dissolving? Right? Okay. So we've done some work on this, okay, and so and this is quite exciting. So what we know, and this is a classic problem, of course, is that the formation timescale to form a bar, okay, here is on the y-axis. But what we've been shown by work we have done, but also Michiko Fuji in 2018, is that there's a very simple relation between the bar formation timescale to develop the bar and the disk mass factor. How much do the baryons dominate over the total mass, right? The dark matter. So if the dark matter is subdominant, it's fast. Okay. If it's not dominating, it's extremely slow, even more than Hubble time. So if the high redshift galaxies have bars, I mean, these objects are only like 1 billion years old, right, or 2. I mean, it's not a lot of time to form the disk and then form a bar, right? So it's a time problem. How can you do it so quickly? And it's even worse, thick disks, which we think these are, thick turbulent disks, they should have even longer bar formation timescales. The arguments by Mike Almer and James Binney, right? So this is not, what's going on, okay? So there's no real systematic study to date on this. There's some work being done. One that's very nice by Zana 2018. I think, Lucio, you were on this paper as well. I think, maybe I'm mistaken, but yeah. And the saving grace here, right, is that when we actually try to tease out the dark matter fraction, right, so the opposite of the baryon fraction within a couple of scale radii, effective radii of galaxies, this is what we have here versus redshift. This is another graph, Pilipich and Hans-Walter-Rix produces plot. They argue that at very high redshift, you can be quite dark matter dominated, but there seems to be quite a large scatter in observations, and indicating also there's a substantial amount of galaxies that are quite dark matter poor, in fact, okay, at redshift of a few. And here, in principle, bar formation can be fast, okay, but we don't know what the thickness does, like the actual turbulence that I've been talking about so much. So the last slide I want to show you here, I think we actually made some efforts on modeling Milky Way progenitors at redshift 3 in isolation, and we set them up in the way that people have done for a long time in isolation. John Dubinsky and Larry Widrow has done this for many, many years, of course. And we want to see now how fast can we develop these bars, okay? And it turns out when we add the turbulent component, instead of slowing down bar formation, it speeds it up a factor of 10 or something. So once you add dissipation, turbulence, you're always unstable on some scale, and you're seeding sort of the bar growth. So instead of a billion-year time scale, after a few 100 million years, you get very strong bars, right? If it's extremely gas-rich, you collapse the bar almost immediately, right? So you create a bulge or something like this, right? And then you create an inner limbless resonance, and you get nuclear disks and something, right? But in some of the other cases, right, where it's slightly more gas poor, the whole galaxy becomes this radial shear flow that's just fueling the central bulge, or also black hole, I would say, right, with gas. Right? So it's a very aggressive feeding of gas to the center in these models. Yeah? So the work in progress we have here is that we like now to understand that connect this to the early universe. Is this a transient phase that galaxies go through? If you start as a pure disk, you're going to be violently bar unstable. It's going to be fast. But it's also going to be very fast for you to transition away from this, because you're going to collapse into a bulge, because you're so gas rich, you cannot support the gravity. So there's a depth of the bar, a change to orbital structure. You get all these kind of things you see in the Milky Way nearby galaxies, nuclear star clouds and nuclear disks form, and likely also it's important for black hole formation. Yeah. That's something in progress. I'm happy to discuss more. But now I've been running out of time since a few minutes, so I'm going to go to my conclusions. Yeah. I talked a bit about the diameter core disks at high redshift. This sort of that James Webb and Allman is revolutionizing the theoretical picture. I've talked about how turbulent can actually disks become, right? Can we trust the data? And most models that we are running now, and I think other groups are agreeing on this, you cannot drive sort of claimed dispersions greater than 50. That's not what disks do. You need something else, than mergers or very fast accretion, something like this. Yeah. There's been a hot debate about the disagreements on these sort of early disks, right? Is it a problem for lambda CDM, all of this? It doesn't seem to be at all a problem, I think. It's just like models have a few differences. It comes down to how we treat the ISM, the resolution, the feedback cycle, these things. So it's not going to be a problem for long, but we have to understand which galaxies or which dark matter halos host these objects. That's important, right? All these Milky Way things we're seeing are the much more massive systems that would be ellipticals. I made some connections to the Milky Way. Thin and thick disks. We have in the stellar population, there's a record actually of this early epoch, and simulations can now be used actually to understand this, so the data here. And then bar bulge formation, yes. So thank you.
Really nice talk, and you talked a lot about the importance for gas cooling, for forming disks, and potentially also for bars. But can you say anything about star formation models and how this can affect disk formation and bar formation? So you're just using a density threshold versus something that's more sophisticated?
I think, yeah, this is a very good point, right? If we go back to the earlier slides on this, right, for example, yeah. So here, there's something that we don't yet understand, right? How can they, I mean, let's start with this one, right? So how can it be that we cannot settle a disk, right, in these kind of models, right? And because even if gas accretion is faster, let's say, right, and your cooling times are shorter, why does the disk react in this way? Right? So I think that is a problem, right? That it comes down to part of this to the treatment of how the star formation is done. Yeah? So we know in these specific models, there's 100% efficiency of converting gas into stars. You just allow the gas to collapse on very small scales. And it's not clear if this means that every star formation event is like a global cluster formation event. Like it's extremely dense, right? So that level of correlation in space and time will lead to very strong feedback. Right? So everywhere you have this bouncing effect, right? And that equates this. So while other models like the one we're doing, we don't allow this process to happen. So we look at the turbulence properties of the gas on 10 parsec scales. We compute what the efficiency would be based on a more detailed star formation model, right? Like Paolo Paduan and also Christoph Federer and others have been doing. So that's what I think the difference is. It seems to be less about the budget. We all agree on what the supernova energy may be, these kind of things, right? But we don't seem to agree on how we actually populate the ISM with stars and how aggressively that's done. And also then there are the more complicated things, the algorithmic part, right? How do you then choose to deposit the momentum, like in what way? That has a bigger effect than we want to admit, I would say. Yeah. So I just say there's more work to be done there, and that is one of the big sources of the differences. This is star formation model.
Yes.
So in your Wintergatan simulations, you actually don't seem to form like strong bars. Is
That's a good point. Yeah.
Yeah. So now like that you did talk about like these idolized simulations where you say like it's more like the set. I guess like mostly the central concentration of or gas concentration in these disks that then like triggers the bar formation or not. Did you check whether that then like in your Wintergatan simulations then leads to the bulge formation?
Yeah, I think this is a very good question. Let me go to these ones, right? Yeah, exactly. So what this would isolate them, right? So now we take the same physics that we did in the Wintergatan simulation, and now we lay out the perfect disks, right? And then we develop this very quickly, right? So the difference, as you are alluding to, right, is the fact that we have what we have done in the cosmological rounds is that we have probably formed too much of a non-disk component, a bulge component early on, and we are also more dark matter rich. So we have blown out too much material, right? And this is a problem. So we don't form bars. We maybe some transit ones, but we really don't form bars. The same problem in fire.
Yeah.
New Horizon is another simulation. They don't form any bars. They found one, I think, for like 2 milliseconds.
Yeah.
And the models that are doing things in a subgrid way, or Riga and TNG50, they form bars, right?
Yeah.
So there's a big difference in how. So once you get a high resolution, there's a propensity for these high-res models to form probably a stabilizing bulge component that doesn't allow the bar to form. I think that's part of the problem. All the outflows are not yet there to do the job. Right? So yeah, there is a problem. Yeah, it should be like it's fine if 20% of the high redshift galaxies have bars for some time, you're fine. But as you run more simulations, they ought to show up, right? And they
Yes.
don't at the moment.
Yeah.
So that's a problem. It's a missing bar problem, yeah.
Yeah.
I think when he asked is really the amount of baryons that you have
Yes.
in a given time.
Yes.
If you delay too much the growth of the baryon relative to the left matter, then you won't get the bar.
Yeah.
In the central region.
Yeah.
Actually, and this is the thing with this is why the underlying population here is actually the TNT50, right? Which is actually is doing a very good job. This is also probably why they have some high redshift bars forming, right? In their model, I think. Yeah. So this is, so we are not, it's one of those things where Pandora's box moment, where you try to go resolving this more and things become worse, right? And the bars is a problem.
Other questions? I have a question about the last major merger and the metallicity, like modality. So I think I agree with the picture, but if you then look at the Andromeda galaxy, right, because there are many reasons to believe that Andromeda had a more recent major merger.
Yes.
Because of bigger bulge, and that's what at least that's what the properties would suggest. Many people have always speculated that that's the case. Would you see a different?
So the Andromeda has there's some IFU data, right, for Andromeda, right, and you can't do results to the populations, of course, right, but it seems to be it's a much more messier, right. There doesn't seem to be any clear bimodality in the Andromeda galaxy. The young stellar populations in the Andromeda is also very hot, right. So the billion-year-old stars in Andromeda is like 50-60 kilometers per second, which is the old thickness of the Milky Way. So Andromeda, I agree. Andromeda is not obvious what it will have, right? But one way to get away from to do this in an extragalactic way is a cervical gecko, for example, right? Where you have the IFU of edge on galaxies, and then you can actually try to look just above the disk plane. What is the the chemistry of those stars, right? To see how common this is. And I didn't put this in the talk, but just to make because I like to create controversy now and then. This stuff here, right? And this is just this. I don't show this to say that we are, we haven't solved everything with our models. It just happens to be something that came out, right? But if you compare different simulation teams, right, on this stuff, this seems to be something very difficult to agree on, right? And it's not because of it's partly because of the hydrodynamical modeling, but it's also because we suddenly have to talk about yield tables and production of elements. Right? So in the Eagle simulations, the early ones, they had nothing like this. No galaxies had bimodality. In Nihao, that our friend Andrea Macho and others are running, all of the high resolution models had something like this. They all had it, right? And then there's a mix in between, right? Auriga has some, Fire had none. They have two now, I think. And so it's very complicated to do the cycling of gas, right? And we don't know what the and you can also see like sorry.
What is the reason?
Yeah. So we don't know the reason for this yet, and the problem to do the exact comparison is also that the way we do star formation in the individual molecular clouds will set the scatter of these relations, right? And we are usually fine with factor of 2, but these 0.1 dex is much less a factor of 2, right? So this is very precision stuff, and we can't get to this yet, I think. Yeah.
One last question.
No, don't do it. No. Okay. The role of the examiner now.
So we talked about high redshifting, right?
Yeah.
So people now, going to insane redshifts, right?
Yeah.
So I mean, like I don't know, 6, 7, 8. I mean, there's no stopping. So when did the first disk galaxies form? Or what are the kind of like, so what is your essentially your own feeling about?
I think I saw maybe this one, like the redshift 7, right? Yeah, and I think if you go to the paper on this one, this has a rotational velocity of many hundreds at this time. So this is forming in a very big. Redshift 0, like group mass dark matter halo or something, right? So they are really probably peculiar objects. It's more interesting to go to these kind of it's a slightly more lower redshift this year, right? And see like are things that are more current day spirals already spirals at this epoch. That's more interesting. But I agree. I don't know what to expect here, but at some point there's not enough time, right? And the merger rates are too high, so I don't see how this can continue. Right?
Yeah, I mean, it also must be then. I if we have many disks at redshift 8, and I work out the part where people argue that the majority of galaxies at a redshift are disks, then this must happen at much lower masses than maybe we even see in the local universe, right? So that's kind of also strange or interesting.
Yeah, I think so. I would say, I agree. We don't know yet the population statistics of this at all. And but one good news, this is all good news for the simulators is like, why is there no data below redshift 4 here, right? Okay. This is, and I mean I had to learn this when talking to observers, right? That the ALMA now, if you want to have the cold gas, like C2, right? The C2 line drops out in band 8, 9, 10 of the ALMA telescope, right? Below redshift 4, right? So it's great for simulators. We can stop the simulation here. We don't have to run it for longer, right? So, but there's an upgrade being done, I think. So we have to keep running the sims a bit longer at some point. Yeah. So, good
I
news.
hope you start the final snapshot.
The what?
I
Yeah.
hope you start the final snapshot.
Yeah.
Okay, so
Anyway.
let's go again for a couple.
I think so. But we have a